Good, how are you?
Good. So what do we got to challenge us tonight?
It's long division again. We have a test tomorrow,
Okay.
and I've been struggling with long division of polynomials.
Okay. You got a problem?
Yeah. Parentheses x cubed plus x squared plus x plus 2, and parentheses divided by x squared minus 1.
All right. You know how if we don't have every power of x represented in the dividend,
Yeah.
that you need to put in a marker, a dummy variable with 0? You need to do the same thing when it's in the divisor.
All right.
So instead of dividing by x minus 1, x squared minus 1, we're going to divide by x squared plus 0x minus 1.
All right.
Okay. Now, what goes here?
Which should be x.
Yeah, so all you do is divide that term into that term, always as a first step in long division. Nothing else matters at this point. We're just dividing x squared into x cubed. So that gives us x. Now we're going to multiply this x times each term of the divisor. So what goes here?
X to x cubed,
Here.
which be 0x squared.
Here.
Negative 1x.
Okay, now we subtract.
Right.
So this is always 0.
Yeah.
What's this?
X squared.
What's this?
This is 0 or 2?
No, it's plus 2x. In other words, what we have is a plus 1 minus a minus 1.
All right.
So it's plus 2x. Bring down the next number. And repeat.
All right. So it should be plus 1.
Okay.
So it'd be 2x plus 3.
That's your remainder. So if I wanted to represent the answer would be x plus 1 plus 2x plus 3 divided by x squared minus 1.
All right.
In other words, that remainder is technically always divided by the divisor. Now, this is kind of a good example of oblique asymptotes. In other words, notice that the degree in the numerator is exactly 1 higher than the degree in the denominator. Well, when you're trying to figure out your horizontal or oblique asymptotes, when you have this exact situation, you go ahead and divide it out, and I don't mean 3 versus 2, I meant where the numerator is 1 more than the denominator. It could be 4 and 3. But if they're separated by 1, then you divide it, and the linear factor you get is the equation of your oblique asymptote. In other words, if I wanted to graph this, Well, I would clearly have a vertical asymptote at both plus and minus 1. And I would have an oblique asymptote whose equation would be x plus 1. Well, that's a y-intercept of 1. It's a slope of 1. There is my grid that I'm going to start with to graph that rational function. Now, when I talk about oblique asymptotes, is that something you've talked about in class?
No.
Never?
I've never heard it.
Okay. Well, let's just go over asymptotes for a moment. Typically, you have horizontal asymptotes. Okay? If I have the following situation, the horizontal asymptote is always y equals 0. In other words, if the degree in the denominator is greater than the degree in the numerator, it's always a horizontal asymptote of y equals 0. If they are the same, like that, then the horizontal asymptote is the ratio of their coefficients, which is 3 to 1. So in this situation, the horizontal asymptote would be y equal 3. Those are the two situations for horizontal asymptotes. And as soon as the degree in the numerator gets to be 1 greater than the degree in the denominator, like that, then you do the division, and whatever you get as a linear factor, ignoring the remainder, is the equation of your oblique asymptote. Now, what do oblique asymptote graphs look like? Well, this is a good grid. Okay, remember I had asymptotes at minus 1 and 1, so maybe it might look like something like this. And then in the middle, it could do most anything. Might do this. And then maybe come out up here. So that could be the graph of this function that we started with here, this initial problem. But always, when your numerator has a higher degree than the denominator, the very first step is to do the long division. So you may not have had horizontal or oblique asymptotes yet, but I would guarantee you that they're coming up next because of this problem that you just gave me. In other words, this problem you gave me was the classic lead-in for oblique asymptotes. All right, what else you got, Mitchell? Let's do another long division one just so we can make sure you know how to do it.
All right. So 5x to the fourth minus 2x to the third minus 7x squared minus 39 divided by x squared plus 2x minus 4.
Okay, let's see, I put my blank in the wrong spot here. Minus 2x third minus 7x squared, and this is the one that needs the dummy variable right here. Is that right? Did I write it correct?
Yeah.
Okay. So help me, what goes here?
5x squared.
Okay. And then get me started here.
So 5x to the fourth, 10x to the third
Plus?
minus, yeah, plus 10x to the third minus 20x squared.
Okay. Go ahead and subtract those. I'll be back in 10 seconds. Hold on.
All right.
Sorry about that. Okay.
Fine.
What did you get?
So it's negative 12x cubed plus 13x squared.
Let's bring down the 0x just as a marker. And repeat.
So it would be minus 12x.
Okay.
So, yeah. So, minus 24x squared. Then plus 48x.
Okay.
$37x squared minus 48x.
Always bring down that next term. And
It's 37.
okay. Well, this one isn't going to end evenly either. Let's see, this is 74x. What's this, 150, no, 148? So let's see, we have a remainder of 89. So my remainder is 89, which really means that it's...
No, it'd be
109. Sorry.
and also 122x. You didn't get rid of the x totally.
You're absolutely right. I'm sorry. And it's minus 122.
Yeah.
I don't know how I overlooked that one. I really got ahead of myself. This is plus there. Okay, so our remainder, instead of writing r equals this number down here, let's write it as part of the answer. There's your answer.
All right.
Now, only question is the sign on this 109 negative or positive? Right offhand, I don't know. Let me think about that for a second. In other words, do I need the parentheses? Once I put the parentheses in, do I need to go in and change the sign on that 109? And the answer is yes, I do.
Wait, why'd you put the parentheses around it?
Well, I thought it was necessary, but I don't think it is now. In other words, how do we figure this out? Well, I know that if I multiply this times that, and then I multiply that times that, I will get this starting polynomial. Right?
Yeah.
I mean, theoretically. Okay, well, when I go to multiply this divisor by this remainder, the denominators cancel, so I'm only left with this. And what sign do I want on that 109? I want it to be positive, which means I've got to make it negative, like that. Now, the reason I put parentheses is because if I don't have parentheses, you see why I need the parentheses?
Yeah.
Because I am subtracting from this quotient this remainder. And it's a binomial term in the numerator and a quadratic in the denominator, so I need the parentheses. And the question is that I want this 109 to be positive when it multiplies. In other words, after this is multiplied by this, denominators cancel out, and I know I want a plus 109. And therefore, I have to make that minus 109 because I've added parentheses. That's a tricky problem. I don't do that much long division by quadratics. In other words, this is a fairly rare problem for me. I'm used to dividing polynomials by linear terms, but you don't ever end up with a remainder that has a numerator with a variable in it when you do that. When you divide a polynomial by a linear term, your remainder always is a number in the numerator. And it's just one term. It's not a binomial term. So that's why this gave me some pause. And in fact, without multiplying it back together again, I'm not 100% sure of this answer. Yes, I am. Let's see. We know that when I multiply this, 5x squared minus 12x plus 37, by this, I need to end up with negative 39. Well, obviously, my last digit is minus 4 times 37, which is negative 148. So I'm clearly going to need to add this 109 to that negative 148 in order to get negative 39. So without doing the multiplication, I can see that this does have to be minus 109. In other words, this thing has to turn into a plus 109 for us to get the proper number.
All right.
All right. What else? That one was a good one. That was challenging.
Just finding the zeros of polynomial function and write the polynomial function in factored form. So.
Okay. What's the polynomial?
F of x equals x to the fourth plus 32x squared minus 144.
X to the fourth plus 32x squared minus 144?
Yes.
Okay. Why is it that we can factor this? In other words, they want us to find the zeros. Normally we can't factor quartics. We can't even factor cubics. You don't have the tools yet to know how to factor a cubic. But there is one thing that allows us to handle this polynomial. It is a quadratic in disguise.
Okay. No.
Now, do you know what I mean by that? Let's use some substitution. I'm going to let u equal x squared, which means if I rewrite this thing as a function of u, I'm going to have u squared plus 32u minus 144. Well, that's a quadratic. We can factor that. We need factors of 144 that add to 32. Well, what's that going to be? 24 and 8? Doesn't multiply to 144. No, it's not 24 and 8. Let's see. Factors of 144 add to 32. Let's see. Let's do this the hard way. We got 72 and 2. We got 36 and 4. We have 8.
36 and 4.
36 and 4 don't add to... Oh, we needed to subtract the 32. Thank you. I was really screwing up there. 36 and 4 work. So if I was going to factor this quadratic in u, it's u plus 36 times u minus 4. Right?
Yeah.
Okay. Well, now let's go back and resubstitute. So that means this thing factors as, instead of u, it's x squared. So it's x squared plus 36 times x squared minus 4. Now, do you see what I've done to do this problem?
Yeah.
This technique called substitution is perfectly valid and very, very common when you get into higher math. You'll use it more and more when you get into calculus and such like that. Now, you don't theoretically need to use it. In other words, is all I need to do to recognize I'm looking at a quadratic is to recognize that this is the square of that. As long as this term is the square of this term, I basically have a quadratic. And it doesn't matter whether it's x squared or x to the 4th or x to the 8th. This could be x to the 8th and that could be x to the 4th, and I would still have a quadratic. And it's helpful to use substitution because it shows you how I can turn this quartic into a quadratic. Notice that this is the same as that as long as u equals x squared. And that's perfectly fine to use substitution and then go back in and resubstitute. In other words, once we have it factored into that times that, then it's really x squared plus 36 times x squared minus 4. Okay, so we're not completely done yet because we didn't find any zeros. Is this going to give me any zeros?
No.
No, that is an irreducible quadratic. If I were to graph that, it would look like this. And it does not cross the x-axis. By graphing that, I mean just this part here. Okay? If it does not cross the x-axis, then it does not have any zeros. It doesn't have any real zeros, this part. This part over here does. How can I factor this part over here?
It would be x minus 4, x minus 2 and x plus 2.
So what are my zeros?
2 and negative 2.
And then there's going to be 2 imaginary ones. In other words, this will produce some zeros, but to solve this, I would set x squared plus 36 equal to 0, x squared equals minus 36, x equals plus or minus 6i. So my 4 zeros, if I want to take it all the way down to complex, are x equal 2, x equals 6i, and x equal minus 6i. Now, frequently, when you are given a cubic or quartic or some higher degree polynomial to factor, it's typical to take it down to this step here, where you have its linear factors and you have what's called an irreducible quadratic. In other words, this would be the typical answer if the question was factor this thing all the way down, rather than coming up with the imaginary solutions of this part of it here. However, on your question, they told you to find the zeros. They didn't say factor it. They said find the zeros. So I would say that this is the correct answer over here. I guess those imaginary zeros count as zeros. In other words, these are the 4 solutions to this chording.
All right.
Okay. Do you have any more?
No.
Okay. Let's see. Are you in school next week, Mitchell? You're not, are you?
Nope. Not at all.
Everybody's out. So what are we doing next week? Anything at all?
No, because I won't have class and we won't get homework because we have a test.
Okay.
So,
let me cancel all 3 of these sessions that I have set for next week.
all right, and then you could probably cancel the one on Saturday too.
Also, okay.
This Saturday.
This Saturday, okay. And next Saturday?
Yeah.
All right. So I will not talk to you again until 6 o'clock Monday, December 1st.
All right.
All right. Well, have a good Thanksgiving, Mitch, and I'll talk to you in a couple of weeks.
All right.
All right. Bye-bye.
Thank you.
You're welcome.